再复一次。没关系。我今天要讲10，不是11些什么10。那我就过去。有啊。
这个是 PDF，然后这边是之前那个 ASS，所以这样可以。
但是我就先用 PDF 上课啊。好。Okay. All right, so welcome back to DSP. Yeah. If I ask you what is DSP, do you have an answer? After all this time we spent together, what is DSP? What is digital? What is signal? What is processing? It's an open-ended question, right? What is DSP? Digital, we know what is digital, right? To represent numbers using computer. Okay, so there will be floating point with integer. That's digital quantization, which introduces error, right? So we talked about analog to digital conversion. So digital is pretty clear. Yeah, the meaning of digital is pretty clear. What's signal? What is signal? Signal is x of n. Okay, signal is x of n. So that's pretty clear too. But then what is processing? That's a part which could be vague. 可能会有点模糊哦。Yeah, what is processing? If I ask you, what do we mean processing a signal? Any idea? 要保证不加分。Any idea? What is processing? All this time we spent together. What is processing? What does it mean to process a signal? All we have learned. What? Filter. Yeah, filtering a signal. For example, we've talked so much about one single thing, right? Low pass filtering, right? That's a kind of processing, very good. What else? Before you started taking this course, what did you expect to learn about processing a signal? Now, this is an open-ended question. So even before we start today's lecture, because this is almost near the end of the semester, okay, so we can just, what does it mean to process a signal? So you see that signal processing is a pretty vague terminology. I'm not sure, I forgot if I mentioned this to you. Signal has a very broad meaning, right? Anything that can change in time is a signal. This is pretty broad, yeah. Discrete time or continuous time. Signal, but processing is a very vague term. What do you mean to process? The verb. Food processing. What does it mean to process food? That means you have material and you have input, you have output, right? The input might be your raw materials. You might be vegetable, meat, fish, eggs, milk, and what else? Yeah, salt, sugar, everything, right? Food processing, and then after processing, the food becomes something that's ready to be eaten. Okay? That's ready for you to eat. To process something, there's input, there's output. Okay, so filtering is a good example. There's input, there's output. So that's kind of the traditional way of if you want to ask the question, what does it mean to process something? There must be input, there must be output. Okay, and in the entire course, the input has been signal, but the output is also a signal. For much of our entire semester, the input could be a signal in continuous time. The output could be a signal in discrete time, and we call this a C2D converter. That's one example of processing a signal. Input is a signal, output is also a signal. And then we have input now being x of n, and we use a difference equation with constant coefficient LCCDE, which is a time, linear and time invariant system, right? So the output Y is obtained by X convolved with the impulse response. We know that. So that's another example of what it means to process a signal. Input is a signal, the output is also a signal. But nowadays more and more people in this field, people in the IEEE Society for Signal Processing, when they talk about processing, they have a broader definition. 有一个比较更宽广的定义啊。They have a broader definition. So I'm not showing a video, but just almost 10 years ago, the society, you know IEEE, right? You guys know IEEE? 国际电机电子工程师协会啊 IEEE. IEEE has different societies. One of the societies is called Signal Processing Society. So about 10 years ago, they defined what does it mean to process a signal. They mean, more generally, it's also possible that when you process signal, your goal, your purpose is to extract information. So signal processing means to extract information from data all around us. So signal now is generalized to all sorts of data. Anything that can be stored can be viewed as signal. Okay, so data is, so more generally to extract information from data, that's kind of a trend. Big data trend, AI trend, you extract information from data around us, not just one-dimensional, but probably two-dimensional images, right? Or three-dimensional video, or any biomedical, like the data from different domain, okay? So nowadays, signal processing is very much driven toward the notion of information retrieval. We want to extract information, or retrieve, 接收, 截取, retrieve. So nowadays, signal processing is more and more about information retrieval. Information retrieval, did I spell it correct? Retrieve. Is it E-I-O-I-E? Retrieve, you figure that out. Information retrieval. So, in the beginning of the semester, I decided that near the end of the semester, we need to talk about this. Yeah. We need to talk about a few examples, particularly in audio. You'll see. So in this week and next week, we'll start from short-time Fourier transform. So the idea is that if the input is, again, a piece of signal, then after some kind of processing, the output becomes information. And usually, it involves transforming your signal into a different kind of representation, okay? Transformation. And today, we will introduce the short-time Fourier transform. So the one quick summary is that in the end, you'll see that we can transform a one-dimensional signal in time into an image, into a two-dimensional image, where we use big X to denote the result after transformation. But now we have two variables. The result might be a function of both time and frequency. So that's kind of the general idea, to transform your signal first into a nicer representation and then start extracting information from over there. So that's kind of the outline and motivation. So here the short-time Fourier transform, but this handout has been uploaded, so you can take a look. So I was trying to kind of motivate you that we need another kind of Fourier transform. Right. For the entire semester, if I ask you DTFT, what is the definition of DTFT? DTFT is to go from time to frequency domain, right? And the result is a spectrum. It's like a 频谱, right? So we've learned that, the discrete time Fourier transform. But I claim to you that DTFT is not useful in many applications. It is not. For example, there's one kind of application called query by humming, and a famous company will be, famous app will be SoundHound. Do you know SoundHound? SoundHound is now selling very well. The market, its stock price has been roaring. It's a company based in the U.S. And does anybody know SoundHound? Have you heard of? Have you ever felt the need that you go to a restaurant, you heard a song, you like it, but you want to know what song it is? So that's. Do you have this experience, or do you have an app that helps you do that? Shazam. Shazam is another company. Yeah. Similar purpose. Okay. Shazam example. So to search, to query, to inquire which song it is, there are two possible modes. One is to just turn on your microphone of your phone, and then let the microphone record the music, the background music, okay, in the restaurant or in the department store or elsewhere. Okay? But another way is to, either way. So this means to query the system, ask the system, what is the song? You can also query by humming. Humming 就是哼歌啦, So if you, somehow it's pretty useful. You can just sing a song into or hum the melody. Just哼歌. Hum the melody. You don't have to be very nice singer. Just sing, and it can at least try to find out what song it is, or what piece of music. By their big database. So that's an example of information retrieval, right? If you think about it. Information retrieval is sing into your phone, which connects to the network, to their server, and in their server, after transformation, you send it to their server and they return information to you. So it's an example, a very good application of signal processing. But I claim that DTFT is not useful. Okay, DTFT is not that useful. The reason is that, at least in the sound world, sounds are not stationary. Sounds are not stationary. Sound just keep changing its content. That's the main problem. And if you look at the definition of DTFT, DTFT is an infinite sum over time. Right? We all know that by now. DTFT is an infinite sum over time. So it goes from time to frequency for sure, but it cannot answer, or it's not convenient for DTFT to tell you if, let's say, if you have a signal in time, and then it goes to the frequency domain, sure, the result is a spectrum, which has a magnitude and also phase, real part, imaginary part. So you can draw a spectrum. And then maybe you see a major component right here, a smaller component right here, right? And this is in the frequency domain. But DTFT does not tell you, okay, what time does this component occur back in the time domain? So there might be a component at, let's say, corresponding to, let's say, 2000 hertz. Okay, what's an example? You go to a frequency domain, there you can see where the energy is concentrated. But now, just by DTFT, it does not tell you what time this 2000 hertz component occurs back in the time domain. It only tells you that there is 2000 hertz somewhere, but it doesn't tell you exactly where, or it's not convenient. It's not convenient as far as visualization is concerned. Okay, so we need to kind of revise our definition and talk about maybe a version of DTF, Fourier transform, which involves some kind of a window. Okay, so a new version of Fourier transform, and then we'll tell you that this new version is called short-time Fourier transform. Okay, it's like developed. It's based upon DTFT, a new version of Fourier transform, which tells you to transform your signal into a two-dimensional representation. Okay, yeah. So another example of signal processing, which just might involve signal that changes in all the time. Yeah? So that's some speech coding over the internet. Speech coding. So I have a lecture of like 2 hours just on this very topic, speech coding over the internet. Okay. Nowadays we don't talk. Do you guys talk over your phone nowadays? Do you talk to your friends over the phone? Do you still do that? Do you text more often or talk more often using your phone? Text. Anybody phone? You still talk to, most time you use your phone to talk to people? or do you use any communication software to talk to people? Discord. 还有呢? Yeah, 还有没有? Yeah. Okay, so for just in case you still use your phone to talk to people, sometimes your credit card company gives you a call, right? You have to pick up. Otherwise, they lock your credit card. Yeah. I don't have my phone. When you talk to, in case you still talk to people over the phone, let me tell you that actually the speech coding standard has been developed so well. So first of all, the compression rate, data compression rate is like more than 30 times. So there's a high data compression rate, and also, so that means that the voice, when you talk to somebody over the phone, your voice is heard by your friend, and your friend's voice is heard by you, right? But the sound is completely, I should say, completely resynthesized on the phone by streaming. 它是一个语音的串流啊，所以那个 the compression rate is high, so that we don't waste a lot of bandwidth in terms of communication. We want to compress the data first. The compression and then decompress. Okay, so there's the coding, encoding, and decoding, which happens on the fly, on both your phone and your friend's phone when you conduct the conversation. It's amazing. It's amazing. It's been highly developed. Okay, and so you can imagine that first of all, now we can ask the question. We're ready to ask this question. Would you recommend using DTFT as a kind of step for speech encoding? Why or why not? Using this, right? Go to frequency domain. Speech is about sound. Sound has frequencies, right? Do we use DTFT directly, like in this format, using this equation? My answer is probably not. Because like speech streaming, you want to process the speech like right away. You cannot wait until you finish an entire sentence and then hit the release button and then send that sentence, right? It has to happen on the fly in both directions. So therefore, this kind of definition is not helpful. This is like processing a file, maybe. You have a file of 2 minutes. Yeah, then you can define the transform pretty well using this equation. But this equation, I want to give you a feeling, it's not so useful when you have an application like this, when your conversation has to be encoded on the fly in both directions. Now, you hate delay, right? You cannot talk and wait for 1 minute until your voice is delivered to the other end, right? That's not the way we handle such situation, right? So delay is an important factor, okay? So in those kind of applications, when delay is an important factor, we need to seriously think about how to process sound, like using one block using block-wise processing, blocks. You want to process sound in blocks. So that means maybe we process this block first, and then deliver it, encode and deliver it. And then the next block comes in, we process the next block. encoded and delivery, and so on and so forth. Blockwise processing, once you wait for a short time, maybe 20 milliseconds at most, then you process the sound right away to extract information and send it to over the wireless network to your friend, to their phone, and so that what happens over there is to decode on the fly. Okay, so you see that to wait until infinity is not a good strategy when delay matters, okay? When processing time matters, when you don't want to experience a lag， 不希望有这些的延迟啊。Okay, so another example is automatic transcription of music. All music and speech are, I say to you, are not stationary. They are not like the spectrum can change in time. So I think in the next slide I do have an example. Okay, so this is an example of actually the result of short time Fourier transform. And on the right, so you see that on the left, this is the result. The two-dimensional representation has a name. We use this terminology spectrogram to call this kind of a representation with time, still left to right. But now the second dimension is frequency. Second dimension is frequency. Is that making sense? I said this makes a lot of sense when you represent music, right? Because otherwise, traditionally, when we think of music, music is something, a sound, vibration that we can hear. And you just study the anatomy, 解剖, the 构造, the anatomy of your hearing organ, the inner ear, and your kind of auditory pathway, 神经的这个连接啊。Fourier transform actually happens along the way. Okay, short time Fourier transform. So so you know that like that's why this makes a lot of sense. You know, musical score, right? What is this domain? This is the time axis, right? Time goes from left to right, and what is this? This is frequency, right? So the Fourier transform, as we'll see in a moment, when we transform our signal into this kind of representation with time and frequency, it actually makes a lot of sense for musical applications. 对于音乐来讲是很 makes a lot of sense. Okay, so for those of you that I need to play this music, but let's switch to, because this is PDF. Okay, we found the corresponding slide in my other course. 对，你要按一下，好。So let me just show you the music, okay? The settings is this is not my computer. 怎么按放映？好。Okay, yeah. So let me play you this piece of music first. Okay, this is 蓝色狂想曲。Sorry for the loudness. All right, so what do you see? You see that there's一个音阶啊 there's a scale, 音阶啊 scale that goes up, right? And here, what do we see? The traces, right? 有些痕迹嘛啊 So here, the way we read the spectrogram is to look at like where, in this example, the dark places. 比较暗的地方啊，比较浓的地方 the dark dense places indicate where the energy is concentrated. Okay, so you see there's trace of a scale going up. So you can read, yeah, information retrieval. Speaking of which, right? So now what are we doing? We have a representation and we start looking at it. So if I don't tell you the score, can you figure out what's going on? That's a task called automatic music transcription, 自动采谱啊。 information retrieval. Like the output now is not another piece of signal but information. Okay? Can you do automatic conversion from the sound first to this two-dimensional spectrogram, then to the score? That becomes an interesting task. It's still not yet 100% solved, okay, up to 2025. So that's another example. So that's a kind of motivation why this kind of transformation and the information retrieval may find applications like such. Okay. Thank you for preparing the slide. So let me go back to my PDF. Right? Where is the PDF? Can you please? Is it here? How? Okay, so any comments so far? Question? Okay, so today's outline. So what's going on? Tony 未预习结束。So we would okay. So to kind of develop into short-time Fourier transform, we need to first talk about DFT, okay? The discrete Fourier transform. And there is a relation between DFT and DTFT. Then we can mention fast Fourier transform and its inverse. And there's the third topic is finally the short-time Fourier transform. And especially there's a trade-off between time and frequency resolution. Okay? It turns out that when you do that transformation, there is an important factor you need to keep in mind. Okay? That is, what's the size of your pixel right here? Pixels. Two-dimensional representations, right? So now in both frequency and time, we have pixels. So there is a frequency domain resolution. Each pixel may occupy how many hertz, right? Each pixel may occupy how many milliseconds. So there is a trade-off between the time and frequency resolution. You can define by yourself. Okay, so that's a kind of important factor we need to keep in mind when we start using when we attempt to plot spectrograms. So. You know what? Actually, I want to jump to C first. I think that's a better flow. Short-time Fourier transform. Okay, so let me just let's jump to the part C first. It's actually easier this way. So now here comes the definition, right? So as I promised, this is the definition of short-time Fourier transform. It's an extended version of DTFT. Now, still summation. So there's a summation over time index n, and the input is your signal x. Okay, the input is signal x, and it involves the usage of a window. And then when you multiply, basically there is a window function, and right here, okay. Surprise if this is the first time you encounter this. Okay, let me finish explaining the equation first. There's a window function. Hahn window, rectangular window, Blackman window, you have learned that. The window function that's applied right here, and then multiply your signal, shift your signal to the left by m samples. Then multiply that result with the window, and the result is a function of n, right? So in the summation, that m is fixed. The summation is over n, okay? So shift your signal to the left by m samples. After that, multiply with the window, and then take the DTFT of the result of the product. Take the DTFT now, the summation index is n, okay? So, and the result becomes, of course, it's a spectrum, but which varies in time, because we are shifting our signal to the left. Okay, so here's a small animation I came up. Okay, I think I do need an animation. Yeah. let me switch back to the. Yeah, sorry for the inconvenience. My laptop has some problem. It wouldn't charge, so that's why I just out of emergency, I needed my TI to help me. 对到这边，对，这个没有改，前面啊，好，谢谢啊。All right. So now a typical window might look like this. So I think this is a Han window. Okay, Han window with zero, with a finite duration. Okay, finite duration, which lasts from time 0 to about 64. There is a length 64 Han window right here, which is used right here. Okay, and so now, so what does it mean to calculate this? Okay, so raised cosine also called Han window right here. But now I want to imagine that your signal is this thing right here. Okay, an actual signal, and then for every n, we are going to start shifting it to the left, like that. So there's an amount of shifting to the left, okay? And at each shift, basically you're fixing the window and let the signal shift. And so when you keep shifting to the left, what does that mean? When you keep shifting the signal to the left, that means we keep looking at later and later part of the signal, right? Because we are looking at the signal through the window. That's the meaning. When they multiply, wherever the window is 0 right there, so that place doesn't matter. All that matters is the part of signal that's in between right here and right there. So when we shift the signal to the left and further, so each time we shift them, we keep looking at later and later part of the signal through the window by calculating the product. Okay, so that's the idea. We keep looking at later part of the signal. That's the idea of short time Fourier transform. Why short time? Short time because this is a short time, only maybe 64 samples in this example. Looking at the spectrum only in a short time. And that's why we call it short time Fourier transform. It's a kind of Fourier transform which uses only a short time, a duration. So you can focus on later and later part of your signal. So now, as a result, the spectrum is going to change as a function of time because you're looking at later m right here. Is that making sense? Shifting the signal so the spectrum can change in time. They become time-varying spectrum. Okay? So this is the way we come up with the spectral, a two-dimensional representation for a one-dimensional signal. Okay, yeah. So this is like 有一句国语的成语叫做，跟这个概念有点像啊，forward 啊 ，forward 白，白什么过什么。中文系白不对，白驹过隙，什么驹？什么驹？一个马。我写简体字，我要写繁体字啊。然后呢，缝隙的隙，哪个缝隙？有听过这笑话？有听过那个张作霖被炸的笑话 ？Gap。A white horse passing through a gap， 戏怎么写？糟糕。小然后小日小，you know what I mean？ 白驹过隙。So this is what I'm saying. What is she? She is the window. Okay. G is the horse. I call this is like a train. Imagine that we are standing. You know, when I grew up, I spent part of my childhood in Banqiao. Anybody from Banqiao right here? Banqiao, thank you. You're from Banqiao. Yeah. I live in Banqiao, so you know there's 县民大道嘛，台北市叫市民大道. You know why there are such two roads? Because underground you have what? The railroad is underground. 县民大道、市民大道. Have you ever thought about it? 台北市市民大道那个高架桥下面是台铁啊。When I was little, the railroad passes right there. 市民大道还有县民大道。所以我那时候住在板桥的那个埔前国小附近的。然后我讲中文啊，那个我以前家里面有亲戚啊，他们家住在对面巷子，对面巷子他们家后面就是铁路。所以一天台铁那主要干，你知道，他火车要经过他家后面多少次，超时啊。然后他们家有个小小的窗户，这么小，那后面就是铁轨，火车经过就So that's this. That's a train. So that's a window, literally a window. 真正是一个他们家的窗户。然后我小时候觉得超羡慕他们的，因为我觉得天天都可以看火车，我觉得。小时候我很羡慕啊，所以 yeah, childhood memories, good old time. So see, window and train. I hope that I help you memorize what's going on right here. We're looking at the train which passes to the left. So each time at every moment we see only one part of the train which is passing by, and then we analyze that part of your signal. Okay, so that's what it means to take short time Fourier transform. So your spectrum can change in time. Okay. So xn plus m with that shift is like train going to the left. W is a fixed window on the ground, so it's like 白驹过隙，一匹马很快，你只能看到马这样子过去啊，白驹过隙的意思是什么？以管窥天，以离侧海，白驹过隙。啊，意思是我不知道什么意思，我忘记啊。Short time Fourier transform. Any question? Any comment? 板桥，你住板桥哪里？哦，比较热闹啊。呀，好。好，我不是很熟，我后来就搬到别的地方去。我在板桥只住了1年多，3岁多的时候，我就印象好深刻，超羡慕那个邻居啊。小时候小孩子真的是很天真的，不会去管说房价或什么的啊，或者环境恶劣，可能那个这些不会，小孩子反而羡慕啊。至少我小时候是这样。好。Okay, so now is your time. Tell me what signal is this? 有点会不会太看得清楚吗？ Can you see the figure clearly? Barely. So this is a short time Fourier transform, a kind of signal. Okay, so in the time domain, we have a sequence of pulses: 1, 2, 3, 4, 5, 6, 7, 8, maybe 1, 2, 5, 10, or 12, yeah, something like that. And fast ones, so the entire time duration is like 1 second right here, and the second, third second, a 3-second long signal with almost 20 pulses of sound. So that's in the time domain, right? So in this example, the time domain, sure, it tells you where the pulses are, but it doesn't tell you actually when you go to your short time Fourier transform. You see the pulses now. 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 right here, and another maybe 12, which follows the 9 pulses. But not only do we see the pulses, but also we get more information right here. What do you see? You see that the energy is kind of, I'm not sure if you can see. Can you see this clearly? Barely? 有看得到吗？看得清楚吗？ All the pulses have an energy concentration near 2000 hertz. Near 2000 hertz. So this is a 2-dimensional representation of a 1-dimensional signal, okay? So you obtain extra information by adding 1 dimension, right? So you see the sequence of about 20 pulses in 3 seconds with energy, with pitch, with the frequency concentration near around 2000 hertz, okay? Does anyone want to guess what sound this is? What is this sound? What is the sound? Huh? Heavy metal music at 2000 hertz? Good one, no. The answer is no. Any other? 想象一下，其实这为什么我今天没有把这个 PPT 给你们了？想卖关子，有修过我研究所课一些，不要破梗嘛啊！在座应该没有人已经修过我研究。Anyone want to make it? So what is the sound like this? 20 pulses in 3 seconds and with a pitch with a frequency of about 2,000 hertz. 我们可以，我今天蛮好奇 ，ask Chat GPT。请说。Bird chirping, that's a good one. Yeah. What kind of bird? No, that's a good one though. Close. Yeah. Bird, I would say it's probably not bird. If you say bird, it's hard for me to imagine that bird would chirp so regularly because it's like almost equal spacing. It looks more like a man-made sound. Than something that can happen naturally. Okay. Beeper. Close. Yeah. Rifle gun. Maybe not, because rifle gun, I wouldn't. The sound is probably broadband. It's loud and broadband. The gun, bullet, the air pressure. Probably not. It probably will not have a concentrated energy near certain frequencies. Yeah. 松鼠，不是，松鼠可能要练过。OK， 所以这也是跟火车有关的。I mentioned 那个亚东医院对不对？捷运的啊，今天怎么都有点大声啊？弄小声，再听一次啊。对不起，我再放一次，小声点，希望能小声点。So I recorded it at Taipei subway. So yeah, so the take-home message today is that next time you go home or you go to Taipei, you can tell your friend, hey, by the way, this is 2,000 hertz. I learned information retrieval using short-time Fourier transform, and you can start the conversation. It's a very nice conversation starter, right? No. It show your friend how nerdy you are. Okay. 听起来就很宅啊。In case, yeah. 好 Yeah, so now here comes the resolution part, okay? The window. So we can use a window, the Hahn window in that equation. Maybe we need to write down the equation somewhere, okay? So we write down the equation. The equation is x now become big X is a function of both omega and m, and definition is still summing over all n. But in fact, in practice, we only sum at where w is not 0, right? Summation reads from minus infinity to infinity, but in practice, you only need to sum up those 64 points, right? Because the window duration is finite, okay? Your window duration is, let's say, from 0 to L, okay? Your window duration is finite, so in practice, or let me just say, for the sake of being clear about this, from 0 to L. L is the length of the window, okay? Assume that the window lasts from time 0 to time L, okay? Shift your signal to the left by m samples, and then take the product, take the DTFT. So that's a definition of short-time Fourier transform, okay? So which involves a window. So here comes the issue, okay? The window is Hahn, use Hahn window, but then there's you need to choose the length right here. You may choose a long window, also a Hahn window with a really long L prime, long length, or you choose a short window, also Hahn window, right? So it's up to you to define what's the length of your window, even given the type of window, okay? So we have two issues. one issue is the length of window, and the second issue is actually which type of window would you prefer, okay? And in this upcoming homework, you have a chance to work on this. But here is a comparison. Same signal, but using different length of Han, okay? 1024 versus 4096, okay? 4 times longer. So when the window length is long, and you're looking at your signal now shifted to the left, your signal shifted to the left, so the effect of using long window is pretty simple. Just you're looking at more points at a time. You're summing over from 0 to a long L prime, for sure. So you're taking in a block of signal, a long block of signal, every time you evaluate the spectrum. That's the meaning. That's the meaning, okay? So but the downside of that is probably the onset is not so clear. The time domain resolution now is lowered because at every moment we use a long window, right? So when the window is too long, then you lose the capability of finding the beginning of your signal, beginning of every with high accuracy. You lose the precision in time. What you lose is precision in time because you're taking in a long block. Okay? For example, if your signal, let's say if your signal is what we just saw, if your signal is just one beep, signal is short but your window is long, and the signal is shifting to the left, right? So in your two-dimensional representation, you'll start seeing something, and in your plot, you see that your spectrum, you see a long area. You see long areas, losing precision in time. You cannot exactly tell what's the beginning time of your signal. I'm not explaining this really well right here. Anyway, so the idea is a long window, you lose precision in time. The signal is shifting to the left, and even though the signal can be short, but if you choose a window that's too long, it becomes hard for you to tell when does the signal start, when does the signal end. Okay, I don't feel I'm doing a good job right here. What do I have? So I have a remark. When visualizing short-time Fourier transform, first of all, we rarely talk about the phase. Okay? Everything here, I should clarify, everything we are looking at so far is the absolute value right here. Okay? So we are viewing the spectrogram by plotting the absolute value of short-time Fourier transform. That's the usual way we do it. Okay? We often discard the phase. So that's just the convention. Okay? Can we agree on that? When we visualize the short-time Fourier transform, we often discard the phase. Second note that time and frequency resolution depends on the choice of window. Okay? The choice of window. So I say that long window leads to loss of precision in time. Long window, loss of precision in time. 在时间上面就没办法看那么准了。讲白是这意思啊。Loss of precision in time. But what you gain is frequency resolution. When we have more points right here, turns out that computationally we don't calculate continuous spectrum. Computationally, we will see a moment that we actually calculate is the kind of discrete version of the spectrum using DTFT. Okay? So yeah, when you have a long window, the take-home message will explain in a moment. Yeah, when you use a long window, you apply fast Fourier transform. So in the frequency domain, the number of points in the frequency equals to the number of the points in time. It's a like one-to-one linear transformation. Okay, so when you have 4,000 points in time for every block, then in the frequency domain, we are looking at 4,000 different frequencies in the frequency domain. So you gain resolution in frequency. You can have higher precision in frequency, but with the sacrifice of time precision being low. So there's a trade-off between time resolution and frequency resolution. When you use a longer window, okay, more points and more points after transformation, the frequency becomes discrete also. Okay, so we'll address this issue right here. Okay, usually computationally, you can imagine that you cannot compute every frequency. We need to discretize frequency. So that's what we are going to discuss maybe for the next hour. We'll talk about a discrete version of Fourier transform. That's exactly by the name of DFT, discrete Fourier transform. Okay, so that's one example. The next example is again, let me lower the volume first. Now I know I need to do this. Lowest, even lower. Let's try this. So now information retrieval, right? Okay, yeah. Make sense? This is what I'm saying. Short window versus a longer window, okay? What do we see right here? Same signal, but same type of window, same signal, but different lengths of window. So we're taking in 1,024 samples at a time. That's the length of window. So as a result, you see like these lines, right? The line right here becomes thinner in the frequency domain. This is more blurry. 这边比较模糊嘛, So that's what I mean losing frequency resolution by going for a short window. But the benefit of doing this is that I argue that the onset, the transition from ba to da, this transition right here is more and more precise, near the boundary of two notes. 两个音符之间的这个 transition, okay? The transition between one note to the next is sharper. You have sharper resolution in time, but here it's not that clear. Clearly in here you have a better resolution in frequency. So that's the difference I want to bring in right here. Same signal, but same kind of window, but by changing the length of window, you obtain a different plot. Okay, so this is something you can choose. You can choose when plotting short time Fourier transform. Okay, so let's take a break. Short time Fourier transform is useful for for retrieving information from sound, because sounds are time varying spectra as we hear them. I argue what you hear when you hear sound, you hear them in as time varying spectra, 会随时间而变的频谱. That's one kind of key message I want to deliver today. Spectra now under this definition can change. A spectrum can change in time. Right? So let's take a break and let's take a break. Yeah.还蛮多的，对。我记得我有删去一些内容。好像只有最后面对对，那个关于 filter 的这次，因为这边就没有教。我今天不，我们这。哎。 对，
那音可能就是再去协调看看。
对了，对了，那轩宇也是也 Hello, hello. Yeah. Okay, so before we start the second hour of lecture, I have a kind of a favor to ask. 希望你们帮个忙啊 I have a favor to ask. So you know that the university, 我用中文好，行政上面，它学校在推动英语授课，当然我们这个课也是英语授课啊。那所以最近这个学校的校务研究中心跟教务处，我有在教务处兼任行政职，所以也是我们希望说，特别请大三的同学，如果你们有修英语授课的话，我们也出了一个问卷来帮助我们评估这学习成效啊。所以那我身为自己本身也是英语授课的老师嘛，那我想说，填问卷大家应该学期末都会被塞很多问卷。我听说啊，有各种的处室单位都会叫你们填问卷，包括教学建评的。By the way, please remember to do that. Okay, let me know where I can still improve. My team can still improve. Please let me know regarding that. But there's a separate questionnaire. 有个另外一个问卷是关于叫做英语授课 EMI 啊。那个问卷的话，如果你们愿意的话，可不可以麻烦帮忙一下？大概3到5分钟啊。如果愿意的话，我把那个 email 的连接。你们应该没有收到，有收到吗？有收到是好。那我个人觉得说这个就当做是相逢就是有缘分。我准备了7本书啊，如果头7个完成问卷，请跟我要1本书啊。好，I will announce it. Yeah, so I pick up a few old books from my shelf. 书架上没有在看的书啊，我觉得说，与其一直放在我书架上，那个还不如就大家交个朋友哦。这样我就可以再去买新的书。So I prepare 7 books for this purpose. Alright, any question regarding お願いします啊，请麻烦大家ください啊。好 so yeah, so during the break, one of you came to me and asked questions regarding details of this plot. Very good questions. Okay, so I want to share with you. So 哪一位？这位后面这位啊，这同学。So you said that you noticed that there's some peculiar things. Here we have a white patch. 有一部分好像白白的，对不对？There's a white patch right here, and maybe also right there. Also, most notably, like above 16 kilohertz, everything's white. So what's going on right here? What's going on right here? What does it mean to suddenly have some empty places? White meaning that there's no signal, right? That like these pixels are replaced by the white pixel by 0. Okay, what's going on? So very good observation. Okay, very good question. And I need to tell you that when I saw this first time, I was surprised too. But later I realized this is because of format. Okay, this is I just took my cell phone to the MRT station and I started recording. But the storage format was MP3. Basically, it's compressed. So you guys probably have heard that MP3 achieved compression. 它达到这个 compression. Achieved compression by a few tricks, and one of the tricks is to throw away unimportant signals. So let's say the MP3 also does an analysis of a spectrum. Look at the part of the spectrum and see that this part is not important. Let's just discard them, replacing this part of the spectrum with 0 to save your storage place. So that's one trick. I'm pretty sure that's what's going on. Particularly everything above 16 kilohertz. I don't think this is the result of analog low-pass filtering. But I think probably after converting to digital, before saving it, before saving the file, my iPhone decided that they look at the spectrum and see that these are not important. It doesn't, even if we store them, it wouldn't affect your hearing. They cannot be heard. Even though the signal is there, if frequency is too high, you cannot hear it. Let's just set all of them to 0. I think that's what's happening. So very good observation, very good question. Okay, missing stuff. If you just record using C2D without compression, you should not expect to see anything like this. You should not expect to see missing pixels. It's almost impossible because the background is always full of noise, right? noise is broadband. So you never expect to see a natural spectrum to have like white patches like that. Okay, that's probably due to compression, right? That's my opinion. Okay. All right, very nice question. So now let's study how the plots are actually generated. Yeah. Because here, please note that even though the time, short time Fourier transform as defined right here, as the definition goes right here, the frequency is continuous. So in one or another, in actual computation, we need to discretize frequency. You cannot compute frequency at every possible real frequency, okay? It's not something that we can store in digital format, right? So somehow we need to discretize, we need to discretize frequency as well. And the correct version to use is called the discrete Fourier transform, or DFT. So let me go back and tell you what is DFT. So now DFT right here, okay? Here we have a definition. We begin with the assumption that we have a block of signal which contains L points. Begin with one block of signal still in time. So time goes from 0 to L minus 1, a total of L samples. Okay. So, but in this notation, by the way, this is my handout, right? So the notation might differ from the textbook, but the idea is the same. So here I'm denoting the block as a column vector. Okay. So S0 to SL minus 1, we have a vector, an L-dimensional vector. That's a way to look at the block as a column vector, right? Transpose. Okay. So far, so good. Now, a block of signal can be viewed as a length L, as a column vector of L dimensions. Yeah, so far, so good. One block of signal. And now, then we define this DFT, the discrete Fourier transform, as a discrete kind of spectrum denoted as big X, bold font, 2 to the S, which also contains L points under this equation. Okay, so let's take a look. So here, K becomes the frequency index. Is that clear? K is a frequency index. And K goes also from 0 to L minus 1. So we have a length L signal, then we are evaluating the spectrum at L frequencies as well. L points in time, L frequencies in the frequency domain. Yeah? So K is the frequency index right here. And so here you see K shows up in here. K times 2 pi divided by L is the actual omega. The discretized frequency equals to K times 2 pi divided by L. That's omega, right? So usually when you look at the Fourier transform, you see the signal inner product, right? What's been multiplied? Usually you see exponential j omega n, right? So here omega is replaced by K times, if you will, the fundamental frequency, okay? 2 pi divided by L. Yeah, so take a look. So you really, we want to contemplate on this definition. Okay, K times in time, K points, K samples in time, K points in frequency. No, K, L. L points in time. L frequencies in the frequency domain, okay, indexed by K. So let's explain why this is called discrete Fourier transform. The terminology could be confusing, right? The Fourier transform, the discrete time Fourier transform, but now to further confuse ourselves, there is a discrete Fourier transform, DTFT, DFT, or simply FT, right? So why is this version called the discrete Fourier transform? Because discrete Fourier transform is the DTFT sampled in frequency. The spectrum was continuous in frequency, but now we sample in the frequency domain. We sample DTFT. Okay, not here. Yeah, basically the idea is to sample DTFT in the frequency domain. So now the frequency also becomes discrete, and that's why we call it the discrete Fourier transform, because the frequency now is also discrete. Time is discrete, frequency is also discrete. Okay, so that's in terms of the terminology. Okay? The reason why we call it discrete Fourier transform. So let's take a look. I have a few kind of visualizations right here. So here, for example, let's focus on left. Okay? So that's the very definition we had in the previous slide. A block of signal which has a length L, and we are evaluating the spectrum at exactly k times 2 pi divided by L, and the result is denoted as big Sk. Frequency also becomes discretized, right? So you can imagine that it's equal to DTFT but sampled at this omega equals to k times the fundamental frequency, oh, 基础频率 if you will, 2 pi divided by L. We say S of omega evaluated at omega equals to k times 2 pi divided by L. I call this the fundamental frequency. So my insight that, DTFT, as we all learned it, you should be familiar now that DTFT is periodic. Every 2 pi, it repeats itself every 2 pi, right? So in this sense, we can say that DTFT is the transform defined on the unit circle. Right? We talked about that already, right? If DTFT exists early in the semester, right? So DTFT is the transform sampled on the unit circle, evaluated on the unit circle. But then now further, DFT is DTFT evaluated on discrete points. So in this plot, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points if our signal has a length of 9. You see what's going on right here? If our signal has a length of 9, a block, if the block length is 9 samples, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we calculate DFT using this definition, we obtain 9 frequencies. 1, 2, 3, 4, 5, 6, 7, 8, 9 frequencies around the unit circle. Whereas if you compute the DTFT of the entire signal by adding 0, by assuming that elsewhere the signal is 0, that's the most reasonable assumption. We say a block has a length 9, and then when you want to calculate the DTFT, so if we assume that everywhere else the signal is 0, then you calculate DTFT, it becomes continuous. It's a continuous spectrum for that. And by doing that, then there's a relation between DFT and DTFT is that DFT is DTFT just sampled in frequency. Is everything making sense? Everything making sense? DFT. That's why. The reason why we call it DFT. Okay. Because it's DTFT evaluated at discrete frequencies. Okay. So with that in mind, so we've seen that I try to argue that DFT is DTFT sampled in frequency. And the other way around is saying, you can say the opposite actually. You can say the opposite, that what is DTFT? DTFT is DFT interpolated in frequency. Let me say that again. If DFT is DTFT sampled in frequency, right? The other way around also makes sense. We can say that now DTFT is DFT interpolated in frequency. Just going between discrete and continuous, okay? That also makes sense, okay? I'm not going to emphasize on this notion. 这个想法，我想先不要过，因为今天第一次接触。I don't want to overemphasize this notion, but kind of the converse is also making sense, okay? Also makes sense. If one thing is the other thing's sample, then that other thing's this thing's interpolation. 一个是取样，大概就是内插嘛。我就当代你 time domain a lot but now we sort of have the situation of doing everything in the frequency domain, right? But what I do want to emphasize that DFT is very simple. DFT is nothing but DFT sampled in frequency. That's for sure. Okay, that's for sure. Easier to understand. Okay. Can I move on? So I just want to bring this up a little bit. All right. So now, more important thing is this concept. DFT, right? DFT is a linear transformation. That's probably the more important message I'm delivering today. Okay? DFT is a linear transformation. You take a column in time. And then the corresponding transform can be represented as a matrix. So DFT is really a transformation from an L-dimensional space to another L-dimensional space. The source space is in time, the target space is in frequency, okay? And the transformation can be represented directly by a matrix. We know that. Linear transformation can always be represented by a matrix, okay? So let's take a look. If small s is in time, big S is in frequency, which is defined as the L frequencies, L samples in the frequency domain, transform, also column vector, okay? Then we can establish, we can construct a matrix, and you can check that this is correct. You can check that this is correct. So you have a small s. If I emphasize it's a vector, small s0 to sl minus 1, which is usually in the real L-dimensional space. And DFT takes it to the frequency domain, S, big S, okay? Big S. Now, is in the frequency domain, also L-dimensional, okay? With this, and you can easily check that DFT is linear. So therefore, any transformation, linear transformation from L dimension to L dimension can be represented by an L by L matrix. L by L matrix. So S equals to, if you call that matrix F, so you can just construct an F such that this transformation now is represented by F. Okay? So let's take a closer look. Here, F has a nice organization. It's all 1 right here, and then 1 if I have this factor W, okay? If I define W as this, nothing to do with a window, okay? W is just a complex number. If I define W with this factor by e to this minus sign j 2 pi divided by L, so, and then we have a very nice organization. It's 1W, W square, geometric sequence for each row, right? The next row is 1W square, W fourth power. Okay, so that's the next row, and so on and so forth. The last row looks like that. Very nice organization. And so to compare, you just check. do we really have sk equals to summation n from 0 to L minus 1 Sn what? E to the minus j k 2 pi divided by L n, right? Yeah. So take a look. This is our original definition, and this is a matrix representation. They are saying the same thing, basically. Yeah. So that basically so you need to ask F. So when we multiply, the trick is to notice that when we multiply a column vector with a matrix from the left, we essentially are doing inner product, right? We're taking the inner product of one row here with a column vector at each time, right? So that's what we are doing. That's what we are doing. So when you say, and what is inner product? Inner product is a summation, is the summation. Okay? So you're taking the inner product, you're summing one row, element of one row, with element of your time domain signal each time for each frequency. You pick a row, do the inner product, and the result is one element in the frequency domain, right? Every element in the frequency domain can be calculated by the inner product, taking the inner product of one row right here with your time domain signal. So it's a linear transformation. So this is like one key notation I want to bring up to you. Fourier transform DFT now can be nicely written in the matrix form. Very nicely written in the matrix form. So is it making sense? Inner product and so on, right? So it's a linear transformation, and it's full ranked. You can check that. So therefore, you can also find the inverse Fourier transform. But here I want to make a few more remarks. First of all, as I said, DFT now with this matrix representation is really, what it really is a linear transformation. And secondly, if you take a look at the matrix right there, you will very soon realize that rows of the matrix, or columns equivalently, they are orthogonal to one another. They are mutually orthogonal. Mutually orthogonal. First of all, this matrix is symmetric. Did you notice? This matrix is symmetric. So row or column doesn't matter. The columns right here, let me say rows. Every one row and another row, they are mutually orthogonal. So basically, now you can imagine that we now have L orthogonal vectors for the space. And for every signal in that space, we are basically doing a change of basis. Fourier transform is the change of basis. We're projecting our signal onto this using the new basis, 用新的基底啊. And they're orthogonal. That's a very nice property. Orthogonal basis is a nice property. It's very nice to obtain an orthogonal basis for your space. Just like X, Y, Z, right? Mutually orthogonal. These rows form a complete orthogonal basis. Is complete. It forms a basis, or orthogonal basis for our space. Every row and any row and any other row are mutually orthogonal. So they are just like X, Y, Z, mutually orthogonal. So which makes them very convenient for calculating the projection. When you have an orthogonal basis, it makes that makes it convenient for calculating projection, right? Because when you do inner product, initially you're doing the decomposition already. 只要算这些内积you're doing decomposition already， 已经把它拆解成这些向量了所以这个 linear algebra notion in Fourier transform I want to bring up. Okay, any comment? 这样有清楚吗？ Fourier transform is easier to explain when we go discrete. Just an L by L matrix. Very straightforward. Okay, so this is matrix representation for DFT, and the matrix is an orthogonal matrix with rows being mutually orthogonal. They're 正交的中文linear transformation, and so therefore, as I explained, DFT is a projection onto a new coordinate system. DFT it is. It is a projection, 是一个投影onto a new coordinate system. 一个新的坐标系A projection onto a new coordinate system, and this is what we're doing. Suppose that we want to evaluate big S at this frequency, right? Taking this second element, for example. When you want to evaluate the spectrum at the first frequency, what we're doing, you end up doing, you're calculating the sum of products. You have your signal as a column vector, and you take this second row and calculate the inner product. Or should I say calculate the sum? Because inner product is a projection. And the result is the result being the spectrum at the first frequency. And we have a few notes right here. Each row represents a basis vector. Okay? And we calculate their inner products with the signal. The Fourier transform now apparently is a change of basis from time to frequency. It's a change of coordinate. It's a projection onto a new coordinate system. And that's what it means to go from time to frequency in terms of linear algebra. Okay? All right. So that's the important idea I want to bring to you. Okay, Fourier transform, the discrete Fourier transform is a linear transformation, and naturally it has a matrix form. It has a matrix representation. You can represent the transformation using an L by L matrix. Okay, are we good? Are you still alive? So how does that relate to the short-time Fourier transform? Okay, so computationally, we are not going to evaluate the spectrum at all the omega right here. We are going to discretize so we are going to discretize and look at k discrete frequencies right here. So that's a connection. Okay, all the plot that you are seeing before, all the nice plots, spectrograms. If you just look really closely, the frequencies were evaluated only at discrete places. Okay, maybe 1024 points. They are discrete. The spectrums are discrete. But now the next topic I want to bring up is that the fast Fourier transform. Okay, bear with me. Fast Fourier transform is actually nothing but a fast implementation of DFT. Okay, so let's try to recall all the terminologies. Right? What is DTFT? DTFT is Z transform evaluated on the unit circle. Okay, and what is DFT? DFT is DTFT evaluated on discrete frequencies. Okay, and then what is FFT? FFT is nothing but a fast computation for DFT. Okay, it gives you exactly the same result but faster. Is that easy? Is that clear? FFT is nothing but DTFT but fast, right? But with a greatly reduced computation load. So let's try to take a little bit of a look. So regarding the computation load, okay, so recall that now we have a matrix representation for DFT, L by L. Okay? The question is, how many multiplications do we need to accomplish one processing of one block? You want to just go from time to frequency domain, L points in time, L points in frequency. Can we agree that this involves L square multiplications? Maybe floating point, L square, right? Because summing the product, summing the product, summing the product, okay? For each element, it takes L multiplications. As well as summation. Then so if you go completely from time domain, L points in time, L points in frequency. Roughly speaking, direct computation of the Fourier transform involve L square multiplications, roughly speaking. That's the order of computation load. 乘法要算 L 平方次啊，大概是这样。It takes L square multiplications to complete one block, processing of one block, okay, to go from time to frequency. So historically, people has asked, is there any way we can reduce the computation load? And the answer is yes. And the result is famously known as fast Fourier transform nowadays. Okay, faster. Actually, it turns out that you don't need to calculate L square multiplications. Yeah, you can reduce the computation load. And tell you the result first. It turns out that it's possible to reduce the computation load from n squared to n log 2n. And that's a lot of saving the time, saving the computation load. A lot of reduction from n squared to n log 2n if n is large. Okay, if n is large. And this, any trick that completes Fourier transform in n log 2n of the computation is generally referred to as FFT, fast Fourier transform. Generally, the computation load is in the order of n log 2n. Instead of n squared. Here n being the length of the block, okay, which is denoted as by L previously. Now, n being the length of f of t. Okay, the paper was published. We mentioned that the paper was published in 1965. 1965, before you were born. And also before I was born, okay, long time ago, 1965. 1965, well, before human landed on the moon, if you will, 民国54年 before the College of ECS of 清华大学 before Department WE, okay, 理学院可能已经存在了，电子学还，工学院可能 I don't know， 电机还没有before 新竹科学园区for sure. Long time ago, it's often named as one of the 10 most important algorithms in history. Often. So sort of as this suggests, okay, n log 2n, so we'll see in a moment that the algorithm is most efficient if n is a power of 2. Let's say n is 1024, which equals to 2 to the 10th power. 如果是2的完整次方数的话，通常会比较有效率We'll see in a moment why. Okay. Any question regarding the kind of summary for the paper? It's often named as 110 of the most important algorithms in history. And its original algorithm is most efficient for if n is 2 to a power. Anybody want to guess what other algorithms are among the 10 most important? 有听过这个说法吗？我没有很仔细想。What other algorithm you have learned can also be listed as 10 of the most important algorithms? How about Parks-McClellan algorithm? No. What other algorithms are also most important? Can you read it? 好，我有学过 quick sort FFT. Okay, I'm not an expert in this domain. Please take 韩永凯老师演算法。I've heard a lot of good words. Right? So this is listed as, if you will, one of 10 most important algorithms in history. Okay, and yeah, let's take a look how the structure looks like. So the idea is divide and conquer. We're not going to go through all the details right here, but if you take a look, what's going on? On the left, we have everything in the time domain, small x. On the right, big X. Okay, yeah, that clear? Yeah. Time to frequency. And now you have routes. The signal goes to the right and also crisscrossing. Okay, so there are, if the length of FFT is 16, which is 2 to the power of 4, right? Or 四次方, right? So you see that just merely by inspection, first we divide. First we have a kind of 8, 16, all 16 to 16 sort of crisscrossing. But in the second stage, what's happening? In the second stage, we are sort of dividing our routes into 2 blocks, right? 2 divisions. This is a one full thing, but then now this 16 is divided by 2. Now the result is 8, right? We have a division of A samples right here, N sample right here. Yeah? So divide, and then we can further divide 8 by 2. Now we get 4 blocks of 4 sample operations. Okay, so one block of 16 sample operation, 2 blocks of A sample operations. Now 4 blocks of 4 sample operations, right? And finally, the 8 blocks of 2 sample operations. And this is just plus and minus. At this point, if I remember correctly, everything that goes down is -1. Everything that goes up is +1. Okay? Divide and conquer. But there's an important detail right here. In the detail, this is where we have multiplication. Otherwise, just plus or minus. Okay? So now you see that everything here, the multiplication happens in between stages. That's an important detail to pay attention to. Okay? So now we have in between every 2 stages. Before we go on to the next stage, we need to perform 16 multiplications by these factors. What is W? W is the W I just mentioned. W is that. W16 is e to the minus j 2 pi divided by 16. And W8 is e to the minus j 2 pi divided by 8, and so on, right? So these are places where we need to perform multiplication. Otherwise, everything else is just plus or minus, adding or subtraction. Is that clear? Divide and conquer. And don't ask me how to come up with that. It must be genius. That's why this is one of the 10 most important algorithms. It's not trivial at all. I don't find it trivial at all. 我觉得并不是非常的显而易见的。Back in the history. Very nice algorithm right here. So let's count the number of multiplications, shall we? Yeah? 数数看有多少个乘法 Shall we? Yeah. Let's count how many multiplications we have right here. 多少个16啊？对，4 stages, right? 3 times we need to compute 16 multiplications. So what's that? So we have 3 times 16 equal to 48 complex number multiplications. Okay? What is 3? 3 is log 2 of 16 minus 1. It's actually log 2 and minus 1, even better. And what is 16? 16 is n. Okay? So the computation load is in the order of n log 2 and actually minus 1, even better for this design. Okay? So that's how divide and conquer helps computing Fourier transform. 觉得有 nice 吗？这个还蛮 nice 的啊。Any question? Any question? 今天应该差不多，就后面只剩一点点啊，后面只剩一点点。我们先讲这个地方啊。So as an example, the longer n is, the better saving you achieve. n 越高的时候，那个 computation 的降低量是越显著。It's more significant to go for a longer n. For example, if length of Fourier transform is only the block length, if it's 8, then it takes 64 multiplications to complete the Fourier transform without knowing FFT, just using the matrix. A squared is 64. So similarly, if the length is 64, then 64 squared is 4,000 something. If you use a direct matrix representation for calculating the Fourier transform. If your length is 1,000, then it's 1 million. But now to compare, if going for FFT, n log 2n equals to 224, 300, or 10,000 for the three cases. So how much do we save? How much computation do we save? You get a feeling, right? So now it probably doesn't save so much. Reducing the load from 64 to 24, it's okay. It's kind of cool. How about reducing from 300 to, reducing from 4,000 to less than 400? Already you have a 10 times saving, by using fast Fourier transform. Even more, for 1024, you don't want to use the full matrix, Please divide and conquer. Then you have 10 stages with 9 layers of multiplications in between. And your computation is just slightly around 10,000, which is about 100 times saving in terms of computation load. Significant saving. So that's why it has a lot of impact. That's one extra thing. And in here, I'm showing just in the textbook. If you're super interested, refer to the textbook. There's an entire there's an entire chapter devoted to fast Fourier transform. There are different architectures. There are different architectures. You can divide and conquer, or I don't know, how do we call it? Merge and proceed. 2 to 4, 4 to 8. You can go the other way. There are different ways to implement that. So this is one of the many implementations. Similar computation load. So what else do we notice? What else do we notice? Anybody? What else do we notice right here? One thing I noticed, and I found it puzzling, I want to point it out before we end today's lecture. On the left right here is x0 to x15, right? On the right, what is the order? What the heck is this order? It's 0, 8, 4, 12, 2, 10, 6, 14. What the hell is this order? How do I memorize this? 我给大家1分钟记得这个 sequence 请把它背起来啊！1分钟背一下，08、42、20，等下抽考就有点。It puzzled me. It really puzzled me. How do I figure out what the heck is this order? By going to a frequency now, fast, but the order is like random. Could that be problematic? 只要记一半 ，How come？ 有吗？你有发现这加起来15是？真的？good。好，那大家请记这一半。那来，然后呢？这半有什么 trick？ 加起来14，那你只要记4个，是这样子吗？你们都太聪明了，好聪明啊，比我聪明啊。So there must be some trick in how this is ordered, But I say the textbook tells us, or any other comment, what this is about. Now you just only need to 记得08，是不是？是这样吗？不是，你还是要记得第2个是8。 你希望我卖关子还是现在就告诉大家？我卖个关子啊，大家这蛮有趣。因为 I think the entire architecture is beautiful. Yeah, it must have something to do with the fact that that matrix is highly organized. That matrix is not random. The matrix form, if we go back, the matrix form is pretty nicely organized, right? So it has something to do with the organization. People have been so clever to discover that we have such kind of this divide and conquer architecture. Or merge and proceed, 合并再前进哦 ，divide and conquer 这我随便编的名词 ，I don't know 啊。So maybe I should end my introduction right here and leave it to you to figure out what's going on. How do we just correctly identify? So it might be easy if the length is 16, but how about if the length is 1024? Right? The last, how do you organize the frequency bin to finally be able to plot the spectrum? Okay? So that's not trivial. Okay, it's important, not trivial and also relevant. 其实是蛮重要的，对不对？好，那 so I guess that's all I want to say about short time Fourier transform converting your signal to an image. And then the definition involved shifting your signal, keep shifting it to the left. So you are viewing your signal by using a window to take a block. So since we're taking a block, so computationally what we actually do is a short time, is a blockwise processing. And now the definition of Fourier transform has to be revised. We have a discrete Fourier transform, which enables us to calculate short time Fourier transform, a discrete version. And the discrete version can be implemented efficiently using any such kind of architecture. Okay, so that will be the summary, and thank you for being here. And I will send you a note regarding 填问卷的事情啊，请大家帮忙一下，帮忙清华大学啊，清华大学拿了不少钱呢，应该这样讲，拿了5400万啊 in case you don't know， 每年拿了5400万要推动学校的英语授课，对呀。So that's why we suffer right here. Hopefully it's not being too bad of an experience, okay? Please help us, right? 好，那 that's it for today. See you tomorrow for the discussion.